Hello, everyone. So this is the Gauss's law tutorial lab. Just like the previous or the first two labs, this one is going to be more like a reinforcement sort of lab or session where you're going to be answering questions that you are going to be going over in the lecture. So what I'm going to do is I'm going to show you guys Gauss's law, how it's used, why we use it, and then you can answer the questions in that lab. And this should also help you to answer the questions in the individual questions. The individual questions at the end of the lab. So the idea with Gauss's law is to use spherical or cylindrical symmetry or any kind of symmetry to compute the electric flux and therefore the electric field of a conductor or an insulator. Now, in the lab and in this tutorial, we're going to be dealing more with conductors. So if you have a charge, positive Q, you can draw the electric field lines. And let's say that I'm going to draw it so you have a magnitude of, all of them are the same magnitude. Like that. So then I can enclose the charge in what we know as a Gaussian surface. Like that. So this is a Gaussian surface with radius r. The electric field due to a point charge is k q over r squared. Vector-wise, in this case, we're getting an r unit vector. You see, you can draw infinitesimal area differentials on the surface of this Gaussian. And you can draw the electric field vector. If this is positive, right? Here's the electric field. So on here, it will be something like this. So 90 degrees. The vector area or the area element and the electric field vector make 90 degrees. But the vector area, which is what you are being asked in the lab tutorial, the future questions, right? If you have a section like this, that's the vector area. I know it's weird to talk about area as a vector because area is just a value, yeah, the surface of a square, a rectangle, a circle. But we need this because when we write Gauss's law, you're gonna find a dot product between the electric field and the area vector. And it comes from this, because the electric flux, which we define with this variable, is equal to electric field times the, here it is, times the area times the cosine of the angle in between. The cosine of what angle? The area vector and the electric field, which you can see are parallel, right? The angle is 0 degrees. The cosine of 0 is 1. So this is basically E times area. What's the area of that? We're looking, it might look like a circle, but we have to think in 3 dimensions. So this is a sphere. The area of the sphere is 4 pi R squared. So if I take the magnitude of this, now capital R, right? Capital R for that radius times the area of the sphere, I get 4 pi k cubed. So the electric flux, the flux 4 pi k cubed. And we call that Q the enclosed charge. So Q enclosed. We define 1 over 4 pi k as the fundamental constant of electrostatics, E naught, the electric permeability of free space, which is times 10. You're going to be using this a lot this semester. That's the electric permeability of free space. So that gives you the value of or you use that to find the value of the electric flux. And therefore you can find the electric field. So what is Gauss's law in integral form, right? So if we want to write Gauss's law, let's write here. That's the introduction, but the equation is the surface integral of E dot area is equal to the charge enclosed over E naught. Why the surface integral? Because you're enclosing the charge on the surface. Now, for a point charge, it's a sphere. And you may have several situations like that, but you can have an infinite line. You can have a cylindrical shape charge. So depending on the type of charge, you may want to use different Gaussian surfaces to enclose. So at the end of the day, you want to see the lines of electric field that are contained in that Gaussian, which is what you are being asked. So in this section here, I have answered quite a few of the questions that you guys have in this lab. How many field lines are leaving the boundary? None of them, right? 0. How many lines are entering or how many are leaving? 4. How many are entering? None. So the number of lines passing through the boundary is 4 minus 0, 4. It's 4 lines. All right. For a negative charge, the difference is that the lines will be towards. So the difference will be that entering is 4, leaving is 0. When you have a negative charge, like we saw in mapping electric fields, for a negative charge, electric field lines go towards the charge. You draw them towards. That's why we normally use a test charge as a positive charge to make it more simple to visualize and explain this. Now here you have another sort of more confused boundary. How many lines are leaving the boundary? How many lines are entering the boundary? Right, so you can see here, be careful with this line here. Can you draw a notch that encloses the charge and does not have the same number of field lines passing through it? So you may have to do something smaller or in a different shape. Okay, so then you're gonna have what we talk about in an enclosed charge and the difference between a charge that has 8 microcoulombs and then one that has 16 microcoulombs. So let me show you what do they mean by that, right? It has to do with this. If you have Q, 4 lines leaving, if this was 2Q, you will have 8 lines. So I'm gonna use other values. If you have, let's use 6 microcoulombs. You have 1, 2, 3, 4, 5, 6, exactly 6. Now how many you have 12? you have double. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you have 6 and you have double there. That's basically the way you answer that question. And then if it's a negative charge, then you have a situation like this. Entering negative, leaving the positive. Okay, so now let's talk about electric flux. I kind of already showed you about the electric flux. But pretty much, if you have a surface, can be a circle with radius r. And I'm gonna just do that general, okay? You have an electric field going like this. How do you find the flux through that area, right? Now, if it's a circle, the area of a circle is pi squared. That doesn't change. So my flux is defined as my electric flux is this symbol phi E A cosine theta. Now we talk about the area vector. The area vector is always perpendicular to the surface. So it's this from here. So I want the angle there. That angle. So if you think about it, that's where the cosine comes from. Because any vector parallel to the surface doesn't give any flux. And you have to answer that question. Think about the definition of flux. What is flux of a vector field? We talk and you talk about that in the lecture on the first day of class. Think about divergence. Okay? Because remember, we can change this equation to the divergence of the electric field by using the divergence theorem. So you can sort of already explain that if I use the horizontal component of the electric field, that's E cosine. E cosine times the area of this. So that's flux. That is flux. All right, and the area vector, I already drew it there as well. And then you want to explain about our area and electric flux directly. I mean, that's pretty easy. Look at the equation there. More area, more flux. This is what I drew on the board. Two vectors have been drawn, labeled. Okay, that's pretty simple, right? Which is the area vector. Just look at the whiteboard, electric field, and area vector. The area vector is always perpendicular to the surface. What is the magnitude of electric? If the angle is 90, cosine of 90 is 0, then that will explain mathematically what happens if the electric field is parallel to the surface, right? So here you have a few common 3D shapes that we use to solve for Gauss's law. Here you're going to look at the electric flux. Think about this cube as one face has the electric field going towards it, and the other face has the electric flux of the electric field going away. So for the one going away, the electric flux magnitude is the same, but the sign is different because it's entering for one, and what happens if it's entering? If it's entering, that means that section of the cube is negatively charged. So then you can realize what type of flux that you're going to have, right? If the charge is negative, think about this equation. Because this is flux. If the charge is negative, the electric flux is negative. Okay? That's the definition. The net electric flux for an enclosed surface is always the charge enclosed divided by E naught. So you can just answer it like that. And for the sphere is what I did at the beginning. When you enclose a charge, so imagine that point there is a charge, and you have the Gaussian surface. You can sort of draw the infinitesimal area, dA here, and then draw the area vector, and draw the electric field. Okay, and then you can explain what the angle theta is and what's the value of it. It's pretty obvious, right? Then that will explain how you go from here to here. What is cosine theta? Okay, so that's pretty much what you have to do. It's a very conceptual lab. All right, so you have to use the ideas I described. You have to draw, and to draw, always assume that the charge is positive. So in that case, it's Q. So the electric field lines go away from the charge, and always perpendicular to the area vectors. That means parallel to the area. Sorry, perpendicular to the differential of areas, parallel to the area vectors. All right. What I think is going to be more important, more interesting is these questions here. Question 1 and 2 are very similar. All right. And it's when you have cylindrical symmetry. Right. I'm going to leave the Gauss' law equation there. And imagine you have a line, a long line with length L, linear charge density lambda. Find the electric field due to that line. There are more questions in there, like what's the value of Q in terms of lambda? Lambda is Q divided by L. But you can also, you probably have done this already in class, lambda is dq over dx. It's a differential, right? So you can use differentials to find electric fields, or you can use Gauss's law. There is symmetry there. It's a very long line. So I can enclose my line with a cylinder. With radius r. So I want to find the electric field at r, at a point at r distance from the line. Oh my God, this is the area, right? This is the area. Charge enclosed. E, the area. So E, what's the surface integral of the area? So the area enclosed by this cylinder is the surface area, right? Which is 2 pi r, the length of the circumference, times the length of the triangle of the cylinder, 2 pi r L. The charge enclosed, lambda L. And I'm pretty sure you guys can finish the problem from there. L will cancel. So it doesn't matter how long the line is. The electric field is always going to be the same. That will help you for the next problem with cylindrical conductors. The same. Cylindrical conductors, you use a cylindrical symmetry. All right? In class, you're going to do more complex situations. So this lab should just help you to reinforce ideas of electric flux, definition of electric flux, area vector, applications of Gauss's law. Nothing out of the extraordinary. Okay? Be careful with this. All right, it was E the area. It's a differential. Anyway, so have a nice rest of your day, guys. I'll see you all in the next video. And send me any questions if you have any regarding this tutorial. Goodbye.